All right, chapter 2 is where things start to get much more kind of in depth, very chemistry, if you will. So we're going to start with the atomic theory, and specifically, they go over two people. First, they start talking about Democritus. So Democritus is around, in the book they said about the 5th century BC, which is around 400 BCE. He's the one who comes up with the idea of the atom, which he calls, well, I've heard it numerous ways. I've heard it pronounced atomo, I've heard it pronounced atomos, I've heard it pronounced atoma. But I just say atomos or atomos. It just means indivisible. Basically, his idea of an atom is if you cut something in half and you keep cutting pieces in half and half and half and half, eventually you're going to get to a piece so tiny you cannot cut it in half anymore. That smallest piece. That is called an atom, which means indivisible or uncuttable. So Democritus, basically his model of an atom is an indivisible sphere. Now, technically, he did have ideas like he thought an atom of iron had little hooks, which is why iron is so strong, is because all the atoms are hooked together. He even thought that table salt, sodium chloride, that atom of that had spikes on it. And the reason why he thought it had spikes was because when he tasted salt, he thought it tasted sharp. But essentially, he thought atoms were indivisible spheres. The problem was there was no scientific way to prove any of his ideas. And in fact, most people did not believe his ideas. Rather, most people believed Aristotle because Aristotle was the most famous person in terms of philosophy. And Aristotle said everything was made from earth, wind, fire, water, and ether. Well, many years later, like over 2,000 years later, about 1808 CE, some textbooks say 1803, it really does not matter. John Dalton was the first to essentially prove the existence of atoms through scientific evidence, and he came up with 3 hypotheses about the nature of matter. First, he said elements are composed of extremely small particles called atoms. Again, nothing smaller than an atom. He is saying that atoms are indivisible. All atoms of a given element are identical. The atoms of one element are different from atoms of all other elements. So for example, down here we have red spheres and blue spheres. The red spheres are hydrogen, the blue spheres are oxygen. So notice they are indivisible spheres. Second, all atoms of the given elements are identical. So notice how all the hydrogens are identical. They're identical in size, in mass, in chemical properties, everything. So every hydrogen is identical. The blue spheres are oxygen. Notice how every single oxygen is identical. However, the second, or I guess the third part, atoms of one element are different from atoms of other elements. Notice the hydrogen and oxygen atoms are different. Okay, they're different in size, different in color, and they'd be different in chemical properties. Second, he said that compounds are composed of atoms of more than one element. In any given compound, the same types of atoms are always present in the same relative numbers. Meaning, for example, here we have water. So water is made from 2 different types of elements, hydrogen and oxygen, and that every single water is made of, well, hydrogen and oxygen. And not only are they made, is every water made of hydrogen and oxygen, but it's always the same relative numbers, which is it's always 2 hydrogens, 1 oxygen. Every single water. The third part says, in a chemical reaction, or a chemical reaction rearranges the atoms in chemical compounds. It does not create or destroy them, meaning if I put a plus sign in between the red spheres and the blue spheres, and then a yield sign, which is an arrow for a chemical reaction, basically what it's saying is in a chemical reaction, these elements just rearrange themselves to make the water. None of the oxygen is destroyed or created. None of the hydrogen is destroyed or created for the water. Later on, we're going to learn that's basically conservation of mass, which we'll see here in a second. So his second hypothesis actually goes for 2 things. It supports 2 things. One, it supported the law of definite proportions. Dalton's second hypothesis is an extension of the law of definite proportions, which states that different samples of a given compound always contains the same elements in the same mass ratio. So notice that it doesn't matter if I start with 123 grams of carbon dioxide, 50.5 grams of carbon dioxide, 88.6 grams of carbon dioxide. It does not matter. If I look at the mass ratio, oh, I spelled ration. I'm an idiot. I'll have to fix that. It doesn't matter. If we look at the ratio, you'll notice that the ratio of oxygen to carbon is always 2.66 grams of oxygen for every 1 gram of carbon, no matter how big or how small our sample is. So this is a law of definite proportions. Carbon dioxide, no matter how much you have, the ratio of oxygen to carbon will always be 2.66 grams of oxygen for every 1 gram of carbon. Dalton's second hypothesis also supports the law of multiple proportions, which states, and this one's a little bit more confusing, this one took me a while to kind of really figure out in depth, which I still don't even know it in depth. When two elements combine with each other to form more than one compound, the weights of one element that combine with a fixed weight of the other are in a ratio of small whole numbers. So what this is saying is if we keep the weight of one of the elements the same, which is in this case carbon, we're always going to have one carbon, always one carbon, but we change the amount of oxygen. So for carbon monoxide, there's only one oxygen. For carbon dioxide, there's two oxygens. We're going to find out that it's basically a small whole number ratio. For carbon dioxide, we notice that the ratio for oxygen to carbon is 2.66 to 1. For carbon monoxide, which only has one oxygen, it's 1.33 to 1. So notice that when we doubled the number of oxygens on carbon, which again, the same amount of carbon stayed the same, the amount of oxygen literally doubled. It went from 1.33 to 2.66. And if you divide that, if you do the ratio of oxygen to carbon for carbon dioxide over the ratio of oxygen to carbon for carbon monoxide, you get a 2-to-1 ratio. This one says 1 to 2 because they did the ratio of this one over the ratio of this one. So they did 1 over 2. In the textbook, they did this one, carbon dioxide on top, carbon monoxide on bottom, so they got 2 to 1. It's still the same thing. So if I was to have a carbon trioxide, which I don't even think there is such a thing as carbon trioxide, at least that's not a polyatomic ion, it would have the following. It would be the ratio of grams oxygen to grams carbon would have been 3.99 grams of oxygen for every 1 gram of carbon. So again, and that would be a 3-to-1 ratio. So notice again that it is a fixed weight of the other in a ratio of small whole numbers. So basically every single time you add another oxygen, you're basically just adding 1.33 on each single time. So that's the law of multiple proportions. The very basic sense of it. I really can't get too in-depth with that. The last part is law of conservation of mass, which is Dalton's third hypothesis, is another way of stating this. Here, matter is neither created nor destroyed. Now, these numbers I just made up. 50 grams of magnesium does not necessarily react with 40 grams of hydrochloric acid. You can do stoichiometry to figure out the true numbers, but I just made these up to prove a point. What he's trying to say here is, Dalton, when you have a chemical reaction, if you start with, this would be a total of 90 grams of reactants, you're going to end with 90 grams of product. 90 grams and 90 grams. You do not create or destroy any matter in a chemical reaction. The mass and the matter stay the same. And that's it for everything for Chapter 2, Section 1.